Hello, welcome back for Sunday morning. Today we have some fun topics today. So neural networks I'm going to start out with. And the attendance will be taken at the first break as soon as I finish this lecture because the TA is not here yet. So we'll wait for her and then we'll do the attendance. Besides, the rest of the class is going to be strolling in anyway while I'm talking. So if we could keep it down, that would be nice. So I'll just wait a few minutes for everybody to stop talking. Hello. Hello. Okay, thank you. All right, so let me get started. So today's topic is going to be artificial neural networks, another AI topic that makes a lot of sense in terms of current research, so it's not a bad idea to cover it. What I'm going to talk about today are what are neural networks themselves. It's not a difficult subject. In fact, I'm not going to get into the nitty-gritty details of designing one. Instead, I'm going to talk about the concepts, just the same way as I talked about the concepts for Bayesian networks and also for other types of AI applications or AI approaches or crossover disciplines. So this is where biology and artificial intelligence meets. So the biological neural networks themselves, artificial neural networks, the basics of developing one, the feed-forward nets. So we talk about feeding forward or feeding backwards. We don't talk about backward chaining or forward chaining because we're not looking at chain reactions and we're not looking at connections between nodes or networks or anything of that nature. Instead, we're looking at a little bit of a different synopsis that goes on between different places of the analysis. So looking at training, neural networks are training systems. Bayesian networks can be trained if you introduce better weights or you put in new information to complement what's already there. And you make sure that you don't have bad data, and you're looking at and you're cleaning up, and you're doing truth maintenance on the network. And the example we're going to look at will be in the area of voice recognition and some of the applications, feeding forward networks, recurrency, Elman nets, Hop nets. I'm just going to give you a brief overview of all those different types of networks to help you out with your understanding of this. So what are neural networks? Well, they model the brain and the nervous system. You don't have to have a degree in medicine to understand them. Computer science use them all the time. It's the model. So it's just like when you do that genetic algorithm for the problem solving that you did for the traveling salesperson. That algorithm was based upon a genetic re-engineering concept, and it applied towards artificial intelligence, and it was used as a platform for the solution to a problem. So is neural networks. So we have the highly parallel kind of system where the analysis is happening all together. So we process the information much like the brain uses it, more like the brain than a serial computer, that is. So it's not a sequential, it's not a network in which we start at the top and we filter down, or we try to pick a path that we like the best, or we go each level at a time. There's no levels to this. Instead, there's connections between nodes, and the nodes are synapses according to the brain, and it really does mirror the way the brain actually kind of thinks, the human brain. And neural networks learn just like the human brain is supposed to learn. So they're very complex principles, very complex behaviors. Put them all together and you can create a fairly robust application with it. So some of the applications as powerful problem solvers and also as biological models, so we can understand the human brain a little bit better. Actually, neural networks are used a lot for thinking through solutions for learning theory. You know, how do students learn? How can you train your dog to not bark? How can you train, a dog to attack versus don't attack? Conditioned reactions. How to get students to learn. It also helps us better understand learning disabilities, such as dyslexia or some of the other ones that are out there. So it's used a lot in science. So in terms of the biological neural networks, it started back at around 1995, which isn't really that long ago, looking at pigeons as art experts. So just like you can train actually you can do this, there's trained monkeys who write better source code than humans do because they're put through a human neural network and they understand the synopsis, well they don't, the computer does, and they process source code faster and more efficient than humans do. Well, what about trained pigeons? Can you teach pigeons to recognize art and, instead of the trained artist? Yes, you can. So one of the experts came up with this famous, it's very well known. Every time you hear about neural networks, you hear about this experiment because this was really the first one that actually proved some some promising results for the future of this concept. Pigeons in the Skinner box. So the Skinner box, they put pigeons in the box, and they have to respond by identifying the potential artists for each one of these paintings that they're going to be shown. So they get shown a couple paintings, and they're identifying it through synopsis that they're making with the paintings to say this is a Van Gogh, or this is a whoever happens to be. I think we have Chagall and Van Gogh actually in the example here, but this is the artist. So presented paintings with two different artists, and they're rewarded for pecking when they're presented at particular artists. When a particular artist shows up in front of them, they peck something, and then they are basically showing that they identify which one it is. So it's a classic kind of, can you teach a bird brain? And the common problem is, you think about it, bird brains are pretty small, but can you teach one to recognize artists? Yes, actually. So you can't teach students how to do this, though, for some strange reason. So if you were looking at the pigeon, he kind of looks like this, and there's, on the left-hand side, there's a little hole, there's a little, like, 2 yes or no responses. So they designed this little pigeon box. This is the Skinner box, by the way, because it was by, the last name of the guy was Skinner. He did a lot of psychological experimentations with animals and things using this particular box. This one's got the pigeon in it. And they had one with rabbits at one point, and one with monkeys in it, and they have different controls that lend themselves better for the different pets or for the different animals. Like, for example, pigeons don't have arms or feet. They don't have the dexterity, so they peck. So they have these little boxes. It says, is this a Van Gogh? And he pecks into the box. Yes, it's a Van Gogh. So he can basically give a response back. And does he understand English? Maybe not. It's a conditioned response. So he's shown a picture, and here's a picture. And he's looking at the picture, and he's supposed to click on the correct yes or no pigeonhole. And here's another picture. And it was actually shown that these two pictures were, you could differentiate the two of them. The pigeons could differentiate the artists of two of them. And then you get shown a third picture of the same artist, or this artist. And then the pigeons could then still identify the correct artist, which is kind of interesting, which means they're not memorizing. So students, when they learn, they memorize. And you do probably haven't figured it out yet, or maybe you have, that memorization doesn't lead to anything. In fact, you forget more often than you memorize. And so if you sit there and go, well, I want to remember this, and I want to learn this subject matter, and I'm going to memorize. Well, if you do like the pigeons did, and not memorize, but formulate the connections between the data, and actually understand the data, without any memorization at all, you have a longer likelihood to remember the data. So what the Skinner box experiment shown that the pigeons were able to discriminate between the Van Gogh and the Chagall. These are the two paintings I just flipped back and forth between a few minutes ago. With about a 95% accuracy when presented with pictures they had been trained on. And the discrimination still was 85% successful for previously unseen paintings by those artists. So because they formulated the data connections and they understood the differences between the two artists, on the ones that they had seen before, you had 95%. On the ones they had never even seen before, paintings they never saw before, you put in front of them, and the pigeons were able to identify with an 85% accuracy. It's only a 10% loss, but it demonstrates how people learn and how humans learn as well. And there's a lot of similarities between the brain synopsis. So if you can take that and put it in a computer program and train it with some data so it has some things it's seen before, and then introduce some things it hasn't seen before, there's a likelihood that you're going to get even more accurate results than in some of the other techniques. So the idea here is to build an artificial intelligence engine that thinks like a human or a pigeon, and train it and expose it to known data, and then test it on unknown data and have it make logical connections and make logical responses given the data. So the pigeons don't simply memorize the pictures they can't. Memorization does not lead itself to understanding or to knowledge, as probably people have figured out so far. So everybody who studied last night and memorized all the different environments and the definitions for each one of them, it's not going to help you on that exam either, because I'm not going to ask you for that. I'm going to ask you to apply it. And when you apply it, then you can test to see if you actually know it. So, because whatever you memorized last night or the night before, you're not going to remember 2 weeks from now. But if you have learned how to apply it and you've made the brain synopsis in a neural network kind of fashion naturally, you'll remember it for the rest of your life, which is kind of interesting. So it's like the value of being a student, learning how to study. The unsuccessful students never really figure out how to study. They don't know how to retain the information. And the unsuccessful neural networks haven't figured out how to capture the right data and how to process the right data to connect it correctly so that the network itself learns and the network itself grows. So we have stupid artificial intelligence programs, and then we also have stupid students who haven't figured out how to study, haven't figured out how to learn. There's an art to learning, actually. So people learn. Actually, does not have anything to do with intelligence. Computers aren't really that smart. They're as smart as the people programming them. Humans aren't that smart either. It depends on, some people are more intelligent than others because they've learned how to condition and how to absorb knowledge and how to apply the knowledge, which makes you more intelligent. But in essence, we're all working on with the same skill set. Biologically, we all have the same thing. So what some people end up being more intelligent than other people, quite naturally, sometimes due to biological reasons, but also due to how they've learned to create their neural network and how they're actually storing and how they're processing and creating connections between people, between neurons. If everybody learned the same way and if everybody was on the equal line, we would not have anybody in prison. We would not have anyone unemployed. We would not have problems. Everybody would be pretty much at the same level, which makes society kind of interesting when you think about it. We're all at different levels because some of us don't have the patience to learn correctly, or haven't learned, or haven't invested the time in learning, so they don't understand. And they have different meanings as well, and they have a different database of information. So the pigeons didn't memorize, so they are extracting and recognizing patterns or the style of the art, and they generalize from the already seen to make new predictions on what they don't know about. So this is what neural networks do. So biology and artificial intelligence are good at, unlike conventional computers, biology gives us the ability to create those connections, kind of like the Bayesian networks, but a little bit more applied towards synapses and connections. So they call them ANNs or ANNs or artificial neural networks, and they incorporate two fundamental components. The biological neural nets themselves, we have nodes and we have weights. So the neurons are the nodes, if you think about this in computer science terms, and the synapses between the nodes are the weights. One weight in a Bayesian network is referred to as a probability. In a neural network, it's more of a known connection. As an example, if you're going back to what I was mentioning yesterday about heat and burning yourself, you create the connection, or the neuron connection with the nodes by associating characteristics of what you might feel is hot with the concept of being burned. The more burning items, the more items that you get exposed to, that you're adding to the network for things that are hot, such as a stove, a candle. All right, so put, hot metal, tea, coffee, something that might be hot in a substance. The more you learn more examples of that, the stronger the connection. The weights go differently because now you don't have to guess about that particular thing, that item. You already know about that item, which is what happens essentially when you study and when you learn. You pick up information. You store the information, and then you make connections with that information with previous information. So if you're storing the information and you have the connection system in place, it doesn't really matter if you've ever seen that item before. You're going to know it's hot, only because you have enough pieces of data to formulate the correct connections to do the synopsis. And the synopsis is the weights. So it's not necessarily, don't think of this, because yesterday I went over Bayes networks and probability. Don't think of this like probability and statistics. This is more connection-oriented or weights. So here's our neurons versus our nodes. In the human brain, I'm not going to pull out a brain to show you neurons, but if I did, it would look something like this picture up here, where we have the cell body, we have the nucleus of the cell, and we have all these different things that connect neurologically and physically our brain itself, which is an organ. And then down in the bottom, we have this network here, where we've got a neurosynapsis occurring. Can we keep the volume down, please? It's not only rude, but it's hard for me to talk over you. And I won't talk, I'll just shut up. I'm going to wait, actually, until everybody's done talking. All right, thank you. You're still talking. They're still talking in the back because they're so engaged in their conversation they can't hear me talk. Thank you. All right, so we have on the bottom here input nodes and output, and we have 1, 2, 3, 4 or 5 nodes coming in. Then we have the sum that's being calculated at the node, which is more of the computer science representation of what we're looking at over here in terms of the nucleus and the cell. So. Then we have the structure of the node, and so we can represent, basically what you're trying to get out of this is the connection between the biology and the computer science. We're taking a biological concept, we're representing it as a computer science concept, and when we do that we have to come out with different terminology. So we have an algorithm, a calculation that occurs at a node. A node is going to be represented by some sort of a data structure. There's going to be a connection between the nodes from a programming level. And we can have a function here, this is the squashing function that limits the node output. So it's kind of like a filter. Something comes in, it gets filtered, and then it goes out. As an example, we filter when we identify. So we have a percept, we have an input, and the input's our eyes. We take a look at the environment, and we go, in fact, if I was sitting here right now, I could take a look at the environment, and I'm going to perceive, and I've got a number in my head of how many students are sitting here. I've got like but I don't have the exact number, but I'm getting the number from the filtering system, because I can physically look at empty chairs versus occupied chairs. And then I can do a we're half here, or we're 100% here, or 2/3 of us are here, and 1/3 of us are missing, or something. And I can filter out, and I can calculate, and I can get that perception that comes out of that experience. Same thing you get when you're driving down the street and you see a ball jump in the middle of the street. If you're familiar with balls and sidewalks and streets, usually there's a child who's with the ball, who is following the ball or running after the ball that's now in the street. And so you can actually automatically formulate that connection without having to do any calculation. So the recognition is pretty quick, and the calculation happens almost automatically. And then we can figure out, well, there's a likelihood that I need to step on my brake. And then our responsive system, our reactive system, goes and steps on the brake, which creates a response to an action. So if we were an intelligent agent and we were using a neural network as our action, condition action kind of response system, we would be able to figure out a lot faster in a real-time fashion what we should do in the particular case, an example of a ball going out into a street or something, which is why it has potential in terms of applications. So synopsis versus the weights. As I was mentioning before, yesterday I was talking about Bayes networks. It's all about weights. We put a weight on a probability that we've calculated, and it's implemented into the system artificially at the beginning. So we create this network, we apply the weight structure to each one of the nodes, we've got the information hard set, and then we run the network. And then what ends up happening is we have the fault of, or the problem of what happens when we create a Bayes network, which is one of the faults is, well, our weights might be wrong, our truth data might be incorrect. And you have to manually go in there and correct the truth data and do what's called truth maintenance, if you remember yesterday's lecture. And you have to go in and fix the problems. Well, a neural network never needs manual maintenance. It doesn't need to be fixed because the weights aren't calculated by statistics. The weights are naturally formulated. As an example, if you go back to human conditioning, you're naturally formulated by your condition versus your nurturing. And going back to what I was saying about math and girls taking math, you're going to go a certain direction if you're female and you're in a math class. You're going to be thinking a certain way and going a certain way given your conditioning, which means if you're told you can't do it, you're not going to do it. And so that's how the conditioning becomes part of the knowledge, and it also becomes part of the weight system. So you get out in the real world and let's say, for example, you don't like a particular topic, so you refuse to take an interest in the topic, or you're told you can't learn the topic, so you don't learn the topic, and you get out there and you have a math problem. You have to calculate something. Immediately, your synopsis is going to have a wrong connection, or it's going to have a bad connection, or it's going to have some learning opportunity where you can add a new connection once you discover what happened with the problem. Was it a problem? You figure out how to do it. It's sink or swim, actually, which is the conditioning people use. So sink or swim comes from the old thing with children. You want to teach a child how to swim? throw them into the pool. They're either going to drown and die, or they're going to learn how to swim. So that's what happens with people, actually. So you get stuck in a situation. Either you're going to learn the situation and how to get out of it, or you're going to die. So survival of the fittest, going back to Darwin's theories. But long story short, when you solve the problem, when you learn how to swim, when you don't die, you build the connections, you build the weights, you build the synopsis through trial and error. So you're going to say, well, okay, I'm going to flap my arms. I'm the kid who got thrown into the pool, and I decided I don't want to die, so I'm going to swim. I'm not going to sink. And they don't die. The parents run in and pick the kid out, and then you know what kind of personality the kid is. If the kid just goes down to the bottom, oh boy, you got problems with that. So if the kid actually tries to swim, then, depending upon how successful they are, you can assist, or you can just let it go. If you let it go and the kid learns how to swim, you're looking at a potential doctor, potential lawyer. You're looking at a very successful person, because that person has the ability to learn. And neural networks and brains, it's all about learning and the ability to learn. Some people don't have the ability to learn. That person will go, oh, and just slip to the bottom and die, which is not a good life quality overall. But long story short, the point I'm trying to make is that as humans, you grow up, you go to grade school, you go to high school, or wherever you do, you go to college, and the purpose of all this stuff in education is to learn. And so once you've learned, you've built to the network, your network's bigger, you have more synopsis, your weights are more accurate, your weights are more correct. Because you learn something the wrong way, and then you learn it the right way through trial and error. And it doesn't really matter how you learn it, whether it's sink or swim or whether it's trained conditioning. Athletes do it through trained conditioning. If you want to win a game, you want to win a track race, well, you run thousands of miles, so you know how to do it. So when you're out there that one time to win, you're going to win, because you're conditioned that way. You know how to do it. It's a learned kind of physical skill. And you have the muscle tone and you have the conditioning for it. Well, same thing with education and jobs. You do better on jobs by learning how to program or learning how to do the information. When you learn how to do the information, you're adding nodes to this network and you're adjusting the weights to use the new information. And what you've got is better connections and more connections. So when you see similar problems, for troubleshooting as an example, you can easily make the connection, solve the problem. You have the tool set already. And so it's easier. So the more you sink and swim, the easier the swimming gets if you're successful at it, which is kind of the theory that goes into this. So synopsis versus weights. Here we have the synopsis, and this is the biological explanation of the neural connection between the two nodes that we're representing here. And the connection that's made in terms of the relationship of the data. Down here we have the same thing, but it's represented in a computer science fashion. So we'd put that into a node system and we would run it, and then we would see what the weights would come out at versus the synopsis. Which leads us to different kinds of network systems and designs. So before we talked about forward chaining and backward chaining and how the network itself is traversed. And it's traversed in a manual fashion, and it's an algorithm that we're saying, if for example we're using Prolog and we're going to put a bunch of stuff in there, we're going to backward chain it actually, but we're going to go from point A to point B going through a bunch of predetermined nodes that exist. Well, in a neural network we don't have chaining, we have connections and synopsis that occurs with weights. So there's a likelihood kind of feeling and connection for the direction. So we call that a feed. We feed the data through, and think of it more like a funnel. Some of it's going to go out this way, some of it's going to go out that way. It's not a direct straight line. And it's not, the connections themselves go through hidden layers of analysis. So the information flow is in a unidirectional. So the data is represented to the input layer, pass through the hidden layer, and then pass through the output layer. So we filter or funnel the information. I always say funnel, but funneling, you get less out. It starts big and you get small pieces out. A filter is usually the same size chunks, so you put something in and it filters and it takes out things you don't want and it continues, which is how we problem solve. We filter, oh, that's not the problem, that's not the problem, that's not the problem, and then we figure out easily what the problem is. Well, that's a synopsis, and actually that's a neural network with a forward feeding net. So for example, you just turned your computer on and it didn't turn on. So the first thing you'd go is that your hidden layer would be, oh, is there power? And so, oh, okay, turn to power. So you plug in your power cord because my computer, the battery's dead or something, right? And then another hidden layer, would come back after the next input would be, okay, it's still not turned on. Okay, so is the power cord connected to power? And then your hidden layer would look for lights. Are there lights on the thing? Oh, okay, we're getting power. And then your hidden layer would go, am I pressing the power button? Oh, sorry, wrong button. Then you solve the problem. The output is the computer turns on and the problem is solved. So you can take and create an artificial intelligence solution with this to diagnose the computer. Well, actually, Microsoft started doing this. It's called a self-diagnosis on the computer when it boots up. So it's self-preserving. So when you boot a computer up, in the old days, I don't know how Windows 8 is, or 7 actually, but there's a safe mode, there's the mode without networking, there's the regular mode, and you can press, I think it's like F10 or F8 or something, and it brings up the menu and you can select. Well, if there's something wrong, you lost the power while you were working on your operating system, as an example, next time you booted it up, it would go through this, oh, wait a minute, there's a problem. We have some lost clusters. And it would go through its self-diagnostic, which is really a hidden layer of logic. And then the output would be, it would loading up in safe mode because it detected that there was a problem. That's an application used for self-preserving networks and self-preserving operating systems. That's actually implemented in a lot of different concepts for computer science. As an example, network security. We can test on a cloud if there's intrusion. We can test data flow. We can test what's coming in, what's coming out, the quantity, the frequency, who's accessing it, how many simultaneous connections are there to it. All this analysis to come back and say, hey, you know what, there's an intruder, or hey, you know what, this is fake, or we have a bottleneck or something. So we can use it for diagnostic purposes in networks, computer operating systems. We can also use it to solve problems in artificial intelligence to come out with, should I buy the stock? Should I sell the stock? There's artificial neural networks being used for stock analysis, for personality disorders, for learning theory. So it has many different applications. Here's what it looks like. So this is the theory behind it in terms of the input, the hidden layer, and the output. So think of this more like the processing that goes on. Here's the feeding data through a network with the input, the hidden layers, and the output. If we put weights on it, one has a 0.25 over here, but this one's a negative 1.5. Well, it's negative because if we went from this node to this node over here, that's pretty far. This node to this node is pretty short, which means the weight says we're going to think this way. So this is like, for example, you think, oh, I have a headache. You wake up in the morning and go, oh, I have a headache. Are you immediately going to take this route on the headache and say, oh, I have a brain aneurysm? Hopefully not, because that's really the wrong way of thinking. And people go, well, how do you know it's wrong? Well, because the likelihood of the weight is slimmer. If you were more intelligent, you'd see this other route over here. It says, maybe I haven't had my coffee yet. Going back to that coffee and the aneurysm, which is the Bayes network example. Maybe it meant I didn't have my coffee. Or maybe it meant I hit my head. Or maybe it meant I'm sick. I have a common cold or something. Maybe it didn't mean I'm having a brain aneurysm, which is where the thinking goes wrong. So it's like, oh, I want to buy a TV. This person over here who thinks, oh, buy a TV, steal it. No, I need a TV, steal it. Versus the shorter path, buy it. Or get a loan first, or get a job first, earn the money, and then buy it. So the synopsis puts the weights on the likelihood not only of the success of the particular action associated with the thinking, but also the morality of it, the rightness, something associated with some characteristic that may not necessarily be represented as a statistic, but it's more of a connection in terms of what is the best result given the nature of humans, which is interesting. Because then you go back and say, well, that's what the problem is. If every human was moral and felt the best results for a human, then we wouldn't have anybody in jail. But we have people who kill other people, we have people who steal, we have people who cheat on their income taxes, we have people who do all sorts of crimes. They're really taking the negative route, which is why we're considering it negative. They're taking the longest path through the system. Example, people who cheat on tests. you know, it takes longer probably to figure out how you're going to cheat. You spend more time in the planning on how to cheat on a test than if you would just study the material. Then that's easier. And then you have fewer risks, and then you also learn better, and it makes the next test easier. But the synopsis of that is the conditioning where people think, oh, I can't pass it, therefore I must cheat on it. Like the guy who can't buy a TV, he has to steal the TV, when he actually probably has the money for the TV, perhaps, depending upon what kind of sale he can find for that TV. Anyway, so the concept is the weights are associated with things outside of statistics. It's not a Bayesian network. What we're looking at is likelihood that it's going to lead to a good result, likelihood it's going to fulfill a goal, provide a utility. There's something evaluation-wise on that. So the data is represented into the network in the form of activations in the input layer. The input layer activates the processing through the hidden layer that gives us our outcomes. As an example, pixel intensity for pictures. There's a hidden layer that says it's supposed to be of a certain intensity, to give a certain contrast, to look a certain way on the screen. Or molecular connections for artificial nose. Or let's say share prices for stocks, stock market predictions. You can predict almost anything using this. So data is usually requires pre-processing, analogous to the senses in biology. Biology we pre-process. We have to perceive, we have to store it in a temporary memory, we have different forms of memory, and then we have to go back and say, well, what is this? And then figure out what it is and apply it towards the network. Because if you don't put it in the context or the terms that you understand, you're not gonna see necessarily the point, or you're not going to understand the synopsis. So the data usually requires a processing, and how to represent more abstract data, a name, for example, might be interesting as well. So choose a pattern. So 001 for Chris and 010 for Becky as a particular example. Might be a pattern of data that leads to a certain conclusion. So then the weight settings determine the behavior of the network because it's the direction that you're going to go in. If our weight system, going back to the television set, if our weight system was moral-based, the percentage of goodness associated with buying the TV is higher than the one that would be associated with stealing the TV. Although some people could put, and some people do put a weight on stealing. It's not a 0 on a moral scale, especially if they think, you know, the person this is the logic actually that goes into some stealing activity. You know, it's like the person's not going to notice, so you're not going to hurt the person. This is all the justification for doing something that's wrong. Or let's say, for example, the person has it too high, therefore I can't buy it. It's too expensive. Or the person doesn't deserve to earn the money for it. You know, all these false assumptions that people make to put weights on the stealing, and then all of a sudden what ends up happening is the stealing weight gets higher than the moral buying weight, so the shift of the network makes them into a thief. They'll go ahead and steal it. Which is kind of interesting because they've interviewed criminals and they go, well, why did you steal the TV? Oh, nobody was looking. Oh. And I say to go, oh, so the weight on the nobody was looking observation made it a higher likelihood that you would do it because nobody was looking. It's kind of like students, you know, how come you cheated on the test? Well, because we were sitting so close together. So a moment of opportunity, you could see it, therefore, because you're sitting so close, okay, so that makes it moral, or it improves the negative, makes it more positive. Okay, so then, you know, okay, well, because it was so hard. Because you didn't study the material? Oh, okay, so because everyone's doing it, which is actually kind of interesting because back when we had that little problem, it was everyone's been doing it for years. It's like, then does that make it right? You know, in terms of the synopsis? So anyway, I'm sorry, it's kind of interesting to see why people make and do things that are incorrect, because what they've done is created a weight system where that's the favor. That's the direction that they're going to go in, because that's the way that they've designed their neural network for the paths in the synopsis to occur. So how can we find the right weights? That's an interesting question. We have to learn somehow. So that's how children find the right weights, and they don't become stealers, they become purchasers. Or they don't cheat, they become honest studiers. So we train the network to learn. So when we learn networks through neural networks, we're adjusting weights. So We're figuring out what pixel intensity is the best. We're figuring out what decision is the best in terms of whether or not we're going to steal the TV or buy the TV. So it determines our decisions because it's in our hidden layer of analysis. So in terms of training, we have this thing called back propagation. So the neural network is designed through back propagation through the learning system. It requires a training set, input, output, in pairs. This is why, as a child, it's always really a good idea to shoplift. Because you're 5 years old, or you're 3 years old. And when you shoplift, you're picking something up off of a table and you're putting it in your pocket. Because you need some adult to tell you that it's wrong. So that, to take, hey, put that back. And you put it back. Kids do this all the time because they don't understand. They're learning that, oh, I want that. So you pick it up and you put it in your pocket because you want to keep it. But you don't understand the monetary system of the American, society. You don't understand you're supposed to pay for it. You haven't gotten the learning yet. So the input is taking it, and the processing is, it's mine now. The output is, oh, I got a piece of candy. So, and that's shoplifting because you didn't pay for it. But you don't know it is as a child until somebody says, hey, that's wrong. Take that out of your pocket. Let me buy it first. Then you put it into your pocket. And so the learning connections are established, the knowledge is gained, the neural networks is created correctly so that the next time it happens, the kid just goes, hey, I want this. And then you go, okay, let me buy it. And then all of a sudden the person learns. So some people say that crimes in America actually are derived from children not learning correctly. So when you're 5, nobody told them to take it out of their pocket. They just left it in the pocket. And then it progresses through life. So the connection is that's okay. Which kind of seems kind of weird, and I'm not trying to find justifications for why people steal and shoplift, but it's amazing when you've seen some of the interviews and you go, why did you do that? I don't know, I've been doing that for years. It's kind of like asking ITU students, why did you cheat? Why do you guys all turn in the same assignment? Oh, because it's been going on for years. That's what we do here. And you go, and that's right? Well, the synopsis is telling you it's right because you haven't been caught on it before. So then you go back to, well, nobody ever caught us before. Well, is that our fault? Kind of, sort of, actually, if you think about it. But it's really your fault because you've been students somewhere else. So we could go back and forth on that. I can go back and forth on that one, but it doesn't really matter. Long story short is the input, the processing, and the output is in pairs. And it's in stimuli, and it's in conditioned reactions. So you start with small random weights, and you build the weights. Pieces of candy to turn into TV sets, which is essentially the issue. The error is used to adjust the weights. So supervised learning. So supervised learning is the concept of adjusting the weights given the outcome. So supervised learning is the 3 strikes rule. So America tells criminals who murder people, well, actually, murder is not a 3-strike. Shoplifting might be. I don't know. I don't know what this is, but on the first attempt when you've been arrested, they say, hey, you know what? This is wrong. And you go, really? I've been doing this my entire life. Nobody ever caught me on this. It's your fault. And then okay, sorry, no, it's not our fault. It's your fault. And then the second strike, when they come in, hopefully it's another type of supervised learning. A good percentage of those people won't come in. Well, you won't see them again because they'll learn on the first try. And then the second time they come in, it's it's more of a, I'm sorry, well, you're not paying attention the first time. The third time is, no pity for you. We're done with you. Because we know we can't supervise learn you anymore. Which means regardless of how we tell you that it should be, it's not going to be. Because you're not going to learn it. Which means that's the justification in the United States for the 3 strikes rule to say, go ahead, give them the death penalty. So, because we're not interested in teaching this person anymore. So we have a gradient descendant on error landscape. So this is kind of what it looks like, where we have to take the errors out of the system to make the good data actually take priority or predominance on the system. It's getting loud again. It's getting loud again. So we have 3 developers here who have worked on this with 3 different kinds of systems. We have Wallace and we have Darwin's. Hello. I'm just going to stop talking until you guys stop talking. Okay, a little bit quieter. All right, so the Wallace-Darwin theory here. So calculating an error, adjusting the weights, calculating an error, adjusting a weight. So back and forth, what they've done is essentially experimented with different types of weight adjustments. This, believe it or not, builds in with theories of evolution. It also builds in with learning disabilities. The diagnosis of learning disabilities is also the foundation for learning theory. It's why we have exams. It's why we memorize things. It's why we don't memorize things. It's the conditioning of the education or the learning of a certain styles. So we have different advantages to learning systems and trained supervision. You're taking a class, this is actually trained supervision. You turn something in, assignment of some nature that you've done, if you've experimented some learning, and then someone's supposed to correct it, or someone's supposed to say, hey, this is right, or hey, this is wrong. And then you build that understanding, and then the next assignment, and you progressively go through levels of difficulty to go from easy to hard. And then that's essentially how you graduate through the learning system, and you're doing self-learning because you're teaching yourself what you're supposed to know. You're being offered supervision through exercises, through exams, through conditioning. And the entire process, they call it education, which is kind of interesting. Child behavior goes through conditioned learning, very similar to education actually, but has different characteristics associated with it. But it also fits into the same kind of concept. So those examples about shoplifting I was giving you sort of fits into the same scenario. If we can adjust the weights, then we can learn. So essentially, learning is adjusting weights on your neural network. So you can come to different outcomes. And what you want is the correct outcome, or the more correct outcome. So that you're trying to adjust the weight so you can. Advantages, it works. Disadvantages, it doesn't work. No, it does. Downsides, there's no disadvantages to it. Downsides might be it requires a required set of training materials. And it's also relatively fast. The more you learn, the quicker you can learn, actually, which is kind of interesting. So the downsides here can be slow. How many people have retaken classes over and over again until they've grasped a concept? Probably in your earlier years, you may not have picked something up quite easily. If you don't pick it up, it goes from being extremely fast to being impossible, or feeling of impossible in terms of learning. Can be slow. Probably not biologically realistic either. And the way that it's applied towards neural networks, you know, it's mimicking biological functions, but it's not realistic in terms of, you know, a complete exact match. So alternatives to the back propagation theory, and the back propagation is the supervised learning through connections and adjustment and error control. So we have the Hopfield learning, we have reinforcement learning, and then we have artificial evolution in terms of learning. So in terms of the Hopfield learning, it's not successful in the feed-forward network. So feed-forward network is when we feed in the inputs. We do the processing and we get the outputs. We can look at the output and turn it around and do it backwards and go to the inputs, which is not feed-forward, it's reverse. So we kind of go back through in an opposite direction. It's kind of like backward chaining, actually. In reinforcement learning, it's only limited success. Reinforcement is no, do it again. No, do it again. It's repetition. It's correction through, I'm sorry, I'm not going to take this. Can you resubmit it? Kind of reinforcement. Or it's, you have to do this 3,000 times because here's your problem set. So we learn math actually through reinforcement. You get it correct, and then you get it correct again, and then you get it correct again. And you go through all the different scenarios to reinforce the concept, to apply it to different contexts so that you can remember it. It's through repetition. Also through negative reinforcement, which is everything everybody is familiar with as a child, because that's very popular. So for a long time, people try to say, well, we don't want to use negative reinforcement anymore. And if this sounds like learning theory, it is. Artificial intelligence, neural networks work with learning theory. It's the basis for most of our learning theories actually out there through psychology. But negative reinforcement says if you do that, we're going to hit you. Or if you don't play well, you're going to lose the game. And believe it or not, negative reinforcement is actually a good thing. So for the last couple of years or so, maybe it's been going on for about 10 years in the United States, people said, oh, let's not use negative reinforcement anymore. So now we have generations of adults out here who have never lost anything before in their life. They have no idea what it feels like to lose because everybody's a winner, which is ridiculous because there are people who are good and there are people who are bad. If you don't know the difference between good and bad, then you're not competitive. You have no idea, no direction. However, you feel better about yourself. So for a while, the theorists were saying, you know, let's teach these children that everybody's a winner. So you have a child's soccer game, and you don't have a winner and a loser. You have two winners. And I'm looking at this going, and I personally didn't agree with it at all, and I'm so glad we don't do this anymore. But for a while, everyone was getting a ribbon. Everyone was winning. And I'm thinking, well, then what happens when the kid goes out there and you throw them into the swimming pool, and they don't know how to swim? They're going to sink to the bottom. You haven't taught them any skills in terms of survival. So they don't know how to win because they've always won. So it's kind of like, you know, it's done with a lot of theory. Negative reinforcement, in my personal opinion, is the best type of learning. Because if you know what you're not supposed to do and you know there's a consequence to not doing it correctly, then you're going to try to do it correctly because you want to avoid the consequence of the negative reaction that's going to occur. So if no one ever had any negative reaction to anything, then that's when you see the kids running around in restaurants screaming at the top of their lungs until some patron comes up to the kid and says, hey, shut up. And then, you know, they start, oh, see, when I said shut up, some of you guys shut up too. That's nice. I'm trying to do negative reinforcement on this class, but it's not working. So anyway, long story short, it's funny actually. People who watch this on YouTube, there was a comment from this weekend actually from a random person on YouTube who posted a comment to my class and said, I don't know how you do it. I don't know why you do it. It's like someone answered the telephone. The other day, I think it was Friday, someone was on the phone, and I stopped to say, hey, are you done with your phone call yet? And I don't think I've seen the guy here, though. I don't know who it was, but long story short, they're like, why do you do this? Why do you put up with this? And I'm like, well, it's actually kind of my little experiment. I've been trying to play around to see what words can I say. How can I control them without controlling them through negative reinforcement, right? So if I tell you, hey, this is on the exam, all of a sudden everyone looks. So I could lie to you all. I could have been lying to you all the last 2 days about what's going to be on the exam and give you an exam that has nothing that I've talked about on it. Because I know you've listened to the stuff I've said. See, now it got quiet again. All I have to do is mention the word exam. I'm conditioning learning you guys. You guys are already conditioned because once you hear exam, everybody shuts up. What? That's what's on the exam. Oh, what? Also, the word shut up actually works. It worked a few minutes ago, too. That works. So, long story short, I'm negative reinforcing you on your positives because you want to do well, I assume. Anyway, long story short, so one of the guys on there said, well, why, that's so rude. I'm like, yeah, it is rude. Why do you put up with it? He's like, it's kind of interesting. It's my own, it's my entertainment. You guys are entertaining me, actually. So, because now I'm learning more about, what kind of conditions. It's real quiet now. So, I'm actually getting more out of this than you are. So it's actually kind of interesting. Anyway, long story short, that's a that theme actually goes with neural networks because you guys are acting the way you're acting because you get away with it. You have gotten away with it. And the rudeness of it is because it's not really rudeness on your part. It's just that you have no interest. And I can say, oh, you have no, get quiet again. As soon as I start criticizing the audience, it gets real quiet. If you guys have no interest, that means I don't have to do it. Because if I'm not going to do it, if you guys don't have an interest in it, right? Which means, I may never teach another weekend class again. So that's a threat, though. That's a negative reinforcement. Because if I don't teach anymore, if I quit teaching here, if I quit teaching you guys won't be able to talk during class. Anyway, now that I've scared everybody, now it's real quiet and paranoid looking right now. I'm not quitting, don't worry about it. But I have 2 classes next term. I'm teaching on the weekends, by the way. So I don't know what they are yet, but I will be teaching next term. So I have to put the positive back in because now everyone in here is like, what the hell is she talking about? What is she talking about? Back to the lecture now that I have your fullest attention because I've entertained you. Anyway, so negative reinforcement is providing a negative. A reinforcement can be done without the negative, then the reinforcement is usually done through repetition, through repeating something over and over again, which is why teachers repeat stuff while students do homework assignments that reinforce things. We also have the concept of artificial evolution. So more generally, you can be seen as a slower than back propagation, but it's also the evolution of what happens. As an example, we've evolved to having a talking issue because it's been going on for semesters after semesters. We evolved to having a plagiarism issue because it's been going on from semester to semester. Well, humans evolved to get conditioned because of behaviors that have been going on from either generations or from other things that might be related to family background or family practices or even society practices in general. So I'm going to run you through an example of a neural network using a voice recognition system and kind of go through how we would build a problem solution for artificial intelligence that involves neural networks through voice recognition. So the task here is to learn to discriminate between two different voices saying hello. So if I said hello and one of you says hello, we'd be able to tell the difference because we're looking at the recognition of the tone, the volume, the pitch, different characteristics. So we have to take and we have to do data representation. And the representation means that we're taking the data, which is the audio tone, and we're representing it in something that we can use for an evaluation from a computer science perspective. So wavelengths actually makes more sense in terms of that. So the data here, the source of the data is going to come from two different people. So Steve and David are the two people who are going to say hello, which is going to be the source. And the format is going to be the frequency distribution in the 60 bins. So the analogy here is, well, we're going to essentially do frequency distribution over wavelengths to kind of see, can we tell the difference? And from a mathematical point of view, we can. We can tell the difference, although if we can get two people, and this happens all the time actually, this is when you have one artist that sounds like another artist. Or, people always say, oh, that song, they stole the song because the pattern or the beat or something is very similar. Well, it is, but it's not. It's slightly different, but when you take it from a data perspective, it looks completely different, but when you take it from an audio perspective, it might sound the same, and then people sue each other over this. But you also can get two people that sound the same. Voices sound the same, tones sound the same, pitches, because we're all human. We're going to produce similar results. But what we're trying to do in this particular network is differentiate. So, and which we can do actually, because the data representation is going to allow us to do that. So in a feed-forward network here, we might have 60 inputs, one for each one of the frequency bins that we're going to analyze, and then we might have 6 hidden layers or 6 hidden input evaluation points, and then maybe 2 outputs. And then one output's going to be, is it Steve or is it David? So we're going to take 2 male voices, have them say hello, look at the frequency information over a distribution of 60 bins, take it through a hidden processing layer, which is going to cross-connect bins. So it's going to look at other data that's going to go, well, they said the same word, it's going to have the same pattern, but there's going to be differences because of the tone or because of the information there. So presenting the data here looks very similar. So in terms of the distribution of the points, this one is slightly different right here than it is here. So then there's our pattern. So now we can tell the difference between Steve and David because of the differences that are going to appear in the pattern. If we were doing a pattern matching, if we're going to do a neural network, we're going to run it through a bunch of hidden layer examples and hidden layer responses. So here's the here's the untrained network, which would take a look and see the differences in terms of the numbers that are going to come out of it. So we can tell essentially on a couple of different scales which one's Steve and which one's David, depending upon the analysis of the hidden layers. So we can also calculate an error or percent error. So this kind of sort of brings in a statistical component into this, meaning we can have a likelihood that it's going to be David versus the likelihood that it's going to be Steve, depending upon how we're analyzing our synopsis. So basically, long story short, the strength of this is in the hidden layer. The better the hidden layer, the better the analysis on the data. If we're just taking the data and doing a pattern match, one data set with another data set, or we're going to run it through a network, like a Bayesian network or something, we're going to get what the data is telling us. If we do a hidden layer, we're going to get what the logic tells us, because the logic is what we're providing that's outside of the data sets that we're going to train to actually produce the better results for us. So we can have a back propagation error, or we can adjust the weights in terms of this case here to come out with a better, 1.17. Well, then that looks like Steve versus an 82% likelihood that it's going to be David in this particular case. Then we can repeat the process. It's called a sweep for all of the training pairs. So what we can do is adjust the weights, send the data in, and see if the results are getting more accurate. If they're not getting more accurate, then remove the adjustments that we put in on the weights and put in new weights, or put in new hidden layer factors, so that when we put the data through, we can actually kind of train the system. So the training can be, and is, with the hidden layers. So we train the hidden layers to analyze the data more accurately. So here, as a repeating process, we're going to represent the data, calculate the error, back propagate the error, and then adjust the weights, and then run the data again, and then see, because what we want is a very low percentage of error that's going to come out of here. So if we repeat the process multiple times, then we get a more even distribution in terms of the output. After we've redone it, we're considering it now trained. So an untrained network uses artificial input that we're putting in for the hidden layer, rules that we're designing, things we're just putting in there. The trained network has the adjustments for the weights that we're going to put in there, so that we can adjust the weights so that we can actually kind of understand more about what we're doing and not take it for strict fact. So it's like, for example, careers. If we look at this career kind of concept and we say, well, on an untrained network, I can say people who like math are going to like computer science, maybe. Or people who like math are going to like music, actually, which is another good connection. If we take it and train it, then we would take and adjust all of the people that are in the room to say, well, not every person who likes math and not every person, is going to be good at computer science. And then when we train it, we add another component in there and say, well, they also like building things, or they're visual learners. Actually, visual learners don't make good computer scientists, actually. They make good UI designers, but they don't make good mathematicians either. So you come in there and you say, well, okay, so now that we have visual people and we add in more characteristic traits in there, then we can fine-tune it to say, well, you might like math. Well, okay, so you might like computer science, or maybe you're more like a software engineer. Maybe you should do software engineering instead of computer science. And it's close. In fact, software engineering and computer science are very close careers. One was right next to the other on a scale between the skill sets, which is kind of interesting. But they're two separate careers entirely. And being a mathematician, that's a separate career as well entirely. So actually, some mathematicians become really good psychiatrists because they study the foundations of all of the theories of synopsis and all of the theories of statistical analysis as applied towards personality traits and stuff like that. And they actually do some pretty interesting psychological stuff. Actually, some of the best managers are really good math people. And they also have, they study psychology as well, so they can apply it. Management is psychology. So, it depends on who you're managing. If you're managing people, you're working with psychology as a base core. And math, actually, is a base core, which is foundation for psychology. Also foundation for computer science and a lot of other careers out there. So a lot of educational institutions, they like to focus on the fundamentals, which is why you're supposed to take this like core classes. You're supposed to take like general education when you go and get undergraduate degrees, because they want you to have a certain math level, they want you to have a certain science level for certain careers, because it's going to help you actually learn the other stuff. The problem is half the students don't understand all that stuff, and they don't want to take the core classes. Instead, they want to jump right into programming, or they want to jump right into, doing autopsies or something, because they want to experience the profession without actually getting the skill set for it. So anyway, learning theory and neural networks is actually a really good crossover. Anyway, if we go back on target here and look at the results. The results here, we have the voice recognition system, where we have the performance of the trained network with discrimination accuracy. Here between the hellos is 100%, and then the accuracy between the new hellos is 100%, which is kind of like going back to the Pigeon example. If we train the network, then the Pigeon's accuracy gets higher. So we can take that 85 by doing a little bit more training and bring it up to 100%. So now the Pigeons will be able to identify different types of artists as well, as long as we've trained them correctly. So the results here, the network has learned to generalize from the original data. And believe it or not, this is how you're learning, because neural networks is mimicking your brain. And so the networks with different weight settings can have the same functionality. And then trained networks can concentrate on lower frequencies and concentrate on the differences, which is how you're going to diagnose problems and how you're going to troubleshoot better. Is because now that you know all of the similarities, and what you're looking for is the deviance from the norm. You know, how are these things different from a minute level? And then the network is robust against non-functioning nodes as well. We don't have to worry about bad connections, and we don't have to worry about things that are bad data. So you put bad data in a Bayesian network, and you've got a bad conclusion. You put bad data in a neural network, and it doesn't affect. It may not actually interfere with the effectiveness of the output, which is how people, you know, if you take language as an example, you have a working set of knowledge that you're working with a sentence structure, which is data representation, knowledge representation in terms of words. You have the meaning or the grammar that's coming out of it, the formation of the sentences and the words. Well, you have bad words. You have words that you shouldn't use, you know, like that are not socially acceptable in certain settings. So we have the memory, we have those bad words in the network, but we have the ability to speak sentences without using those bad words, and they don't come up as bad word choices because we've trained the network well enough so that we can get 100% accuracy with no bad data. So the bad data is there, but we're not using it. It's not necessarily bad data, it's just inappropriate data for the purpose that we're using the network for. So anyway, so applications of the field-forward networks, pattern recognition. It's used for picture matching, it's used for voice recognition, signature, handwriting recognition, character recognition, face recognition. You can put together a neural network to identify somebody's face for a security program. Also, we'll do fingerprint recognition, palm recognition, all sorts of different things. Sonar mine or rock recognition. So in 1988, they used it for mining and for rock formation, you know, to recognize outskirts areas without having to dig down. So you can come up with an artificial intelligence solution that can easily identify or recognize something that it would take a human days or months or years to actually kind of figure out. Navigation of a car as well. You can use a neural network to drive a car, actually, given all of the inputs. And then it can work because it's fast, it's real time. So if we thought like computers, so it was just funny, a lot of humans think that computers are intelligent and that computers think quickly. They don't. We think faster because we're using more of a neural network architecture. Computers aren't working with a neural network. So we can't put a navigation system in using a traditional style program without using some sort of an artificial intelligence engine with that can quickly determine to accelerate, to brake, to turn left, to turn right. Stock market predictions also. Pronunciation, net talk. It's used for pronunciation, which is actually kind of an interesting thing because Siri is doing a neural network analysis on the words. So you have text-to-speech recognition or translation, where you have a sentence, which is kind of the interesting thing. So if you think about old computer, artificial intelligent, old speakers, old natural language processors, sounded like a computer. The car is in the garage. Or it says, hello, thank you for calling Barbara. It just says, it's all different patterns, different tones. It doesn't sound like a sentence that's been put together. Now we have things like Siri, and we have things like, you know, artificial intelligent natural language processors that are using neural networks to process the sentence to read it like a human. And it's actually mimicking a human because it's going, the first part of the sentence, the last part of the sentence, and it's putting it together in a natural language, systematic kind of format so that it's delivered quickly using a neural network application that's coming through and analyzing which word is coming before which other word, so it can say, the car is in the house. Actually, I didn't even say that right. Or, the car is in the garage, to use the correct tones on certain things versus other ways of saying the sentence. So you can use a natural language process. You can use artificial neural networks with natural language processing, long story short, to create more human realistic pronunciations and recognitions. So cluster analysis here on a hidden layer, which you've been looking at for the rock example, where you have the mine echoes, the rock echoes, and you have all of the different faces here. These are examples of those sample applications that I was talking about. So you can do face recognition, male, female, have different groups of people out in these different categories. Also identify non-faces. And then you can measure the dissimilarity or distances between the vectors here as an example as well. So you're measuring, what matches and what's different or what doesn't match, which is what we do naturally. So if I were going to give you, as an example, most people don't know what the dollar looks like, but you can tell a fake instantly. But you don't know what if I were to ask you what president is on the dollar bill, about maybe 2% of you would actually be able to answer that question. Or what information is on the dollar bill. But if you saw a dollar bill, you instantly know it's a dollar bill. But you can't even identify what words are printed on it. You don't even know what it looks like, actually. It's pattern recognition. If you saw a fake dollar, and you're going to pull out a dollar bill, okay. What president? Actually, that'd be a nice test to give you on an exam. Everyone would fail it. If you saw a fake dollar bill, instantly you go, oh, that's not a dollar bill. Well, how do you know it's fake? You don't even know what's on it. How do you know that that's fake? It's because your pattern recognition and your neural network is looking at it and it's processing it, and it sees something that doesn't match correctly. It looks at it and it's not familiar. So when you take a dollar bill and you crumple it all up and it gets all really fuzzy or something, you look at that, is that really a dollar bill? What's wrong with that dollar bill? Or if you see a fake one, instantly, it doesn't even matter. You don't even have to know what's on it, which is actually kind of funny because people will pull out a fake bill or something that's been crumpled up and compare it with a real one. And you look at that going, wow, that's what a dollar bill looks like? Which is kind of amazing if you kind of do that. Then you go, wow, I use this, a dollar bill is a good example because you use it every day. It's quarters, huh? Oh, that's a good excuse. You carry credit cards and debit cards so much you don't see money anymore. Perhaps that might be a reality of the future, actually. Yeah, well, that's a good point right there. You don't know what's on your credit card either. You don't know what's on the debit card. You don't pull the debit card out and say, what does it look like? Blue, green, black. But what's on it? Is your name on it? Is the card name on it? Is the address bank on it? There's probably going to be a telephone number on the back. Most people will know that the information's on there. And it's okay, your driver's license. What's on your driver's license? Does it actually have your hair color or your eye color on it? Yeah, it does. So you know that because you have used it for that before. So. All right, well, and my point is we look at it so often we don't actually know what it looks like. So another classic example is when, like, say, you have something like your dog or your cat or your pet, and you see that thing every day. You don't know if it's sick. You don't know if it's gained weight or lost weight. You don't know if it's because you can't see it because your mind doesn't see it. You process the information through a neural network so quickly. It's an object. It appears, but you don't see it. Okay, so let's see, what do we got here? Biological models for forward-feeding networks. This is what the FFN stands for. We have signaling, and these are some examples, again, going through more examples. Ernst and Arc, 1994, not too long ago, actually. The preference for a symmetry, not selection of good genes, but instead arise through the need to recognize objects or introspective of their orientation. So we're going to essentially look at the symmetry of things in terms of it not being black or white or good or bad, in terms of gene analysis, exaggerating, maybe ornamenting, facilitating mate recognition for Johnston. There's a couple of different people out here who have been researching artificial intelligent networks. But this particular subgroup has a few more examples. So you can go online actually and look it up and see all of the different applications for artificial neural networks. Some of them are using it for, it's different than genetic algorithms as we've seen, but you can use it for genetic predispositions in analysis because you can run it through a neural network as a model and sort of see where the mutations are occurring or where changes are occurring in the patterns. So recurrent networks, also used for feed-forward networks. This is a different type of artificial neural network. So for feed-forward networks, the information only flows one way instead of flowing multiple directions, and one input pattern produces only one output pattern. So the classical example is you have many inputs that produce many different outputs through the processing, and then they can flow in any direction that you want to flow in. With a very focused one-directional, you put things in better context because you're only looking at the context of one direction. So no sense of time or memory of previous states is required for this. And then the recurrency, the nodes connect back to other nodes or themselves. So they're definitely focused. And the information flow is multidirectional. And then the sense of the time or the memory is of the previous states, which is more on the lines of occurrences, which is basically our Bayes networks, our connection between our occurrences, which is where we're getting our context of a solution for recurrency. So biological nervous systems show a high level of recurrency, but feed-forward structures exist as well. So it's kind of an interesting topic to kind of consider how our biological system works. But we definitely are a recurrency model. We have connections to other nodes and other nodes to themselves. Going back to the heat example, that's a recurrency example. So we know the connections between hot and cold. We know between burning and not burning. And it's by occurrency. So if we have a reoccurrency approach, what we're doing is we're taking and analyzing the connections there. So Elman net's another variety of artificial neural networks for your complete survey here this morning. The networks themselves are feed-forward networks with partial recurrency. So we have the output inputs that are coming into the units that are coming into the hidden layers. All of these work with the same concept. We have the inputs, the hidden layers, and then the outputs. So unlike the feed-forward networks, the Elman networks have a memory or sense of time. So we can figure out how long, how many occurrences have there been, how long have we been testing this, and use it for accuracy or use it for something else. So, classic experiments on language acquisition and processing from Elman's and Elman's. Experiments themselves have led to different types of networks that are characterized by his memory and, by the characteristics of the forward feeding and the memory and recurrence and partial recurrence that exists. The tasks themselves, the ELNet is to predict successful words and sentences. So in terms of word analysis, we can say that frequency of use of certain words and the way that the person speaks in terms of vocabulary preferences, people will say things a certain way. So his analysis was on a study of sentence construction and how humans put sentences together, which is actually kind of interesting because everybody in here talks a different way. You'll have different sentence structures based upon your neural network that is deciding your frequency and your preferences on words. And believe it or not, there's another guy out there, a scientist, who goes out and says, well, it has something to do with the biological structure of your mouth and the length of your tongue, the thickness of your tongue, your diet that leads to saliva, and the existence or non-existence of saliva. All those factors play into, when you were a child, how you formed your neural network to develop your speech patterns, which is how some people have speech issues. They talk in certain ways, and some people have learned and have retrained their network so that they hold their mouth. In fact, this goes into our singing class, to train your mouth to speak through your larynx and your upper and your lower larynx, and all the theory that goes into formation of words and sound. which people have to learn naturally. You don't wake up in the morning on your first day of life and get voice lessons. You learn how to do it through trial and error, and it's all your natural way of doing it until you get into grade school and they notice a problem. They go, hey, you have a lisp, or hey, you have a this, or you have a that, and then they start correcting it. But if there's no correction, everybody in here is a product of your own neural network design, which is coming from your recognition, your pattern, your synopsis, everything you've created. So, in his experiment, he took it and tried to create an artificial computer neural network to mimic the human neural network that we've all developed. So the task was to predict the successive words and sentences and how the patterns are going to work. The data was a suite of sentences. So the boy catches the ball, the girl eats an apple. That's two examples. And the words are input one at a time. And then we have the representation in a binary format, or something computer readable, to say that the 0, 1, 0, 0, 0, for example, represented the girl. And then we have the training method, which is going to be using back propagation that we've looked at already. So the internal representation, we have the verbs, the nouns, the adverbs, the adjectives, all the different pieces of the sentence that can be put together. And then we have the different learned sentence structures. So in an artificial neural network, we can actually implement those in. In your own networks, you've learned your own structures. And not every person in here has the same database of sentence structures that you use. Some people have a limited sentence structure. Some of them use, non-popular ones. Some of them use things that have been taught through listening, through audio learning. So, in fact, that's interesting because a lot of people say, going back to this concept here, a lot of people who learn foreign languages watch TV. And you see that the television structures and the way of speaking is a lot different than real life. So they talk like they're on TV, which is kind of funny, actually. If you've ever seen someone who's come, a foreigner, well, you guys are foreigners, so some of you actually talk like TV as well. It depends on how you learned English. Because the TV sentences, totally different than real life. Because it's acting. It's the way you're represented on TV. So it's just kind of funny, because now you can tell TV. In the old days, you used to be able to tell TV from real life by listening. Now it's actually similar. The similarities are, because of the understanding of the concepts, the similarities have become very more frequent. There's very few dissimilarities. So now you can actually have a television show that actually sounds like the real world. But in the old days, it never used to. So. But yeah, those people who learn English by watching TV sound like they're on TV. It's the expressions that they're using and the way that they're talking, it sounds like a punchline, or it sounds like a joke, or it sounds like, sitcom. Like, wow, I didn't know you could do that. You're like, who says that every day? You don't pronounce the sentence like that. You go, wow, I didn't know you could do that. In a regular kind of sentence. So we have Hopfield networks. So those are subtypes of the recurrent neural networks that we looked at. And they're fully recurrent, which means they have a lot of repetition and regurgitation in there. And then they're also, weights are symmetric, so they're balanced. And the nodes can only be on or off. And we have random updating versus learning systems that we looked at. So. Also, it's called learning the Hebrew, which the cells that fire together, wire together in terms of the concept, and it comes from the biological equivalences of the synopsis, and it's more mimicking human brain synopsis versus artificial implemented techniques. So it can recall a memory, and if it presented with a corrupt or incomplete version, can actually complete it. As an example, this is how we fill in the blanks. So as an example, when you get into a car accident, the car drives away, and the first thing the police officer asks is, did you see the license plate? Well, what you're doing is you're doing this kind of synopsis. You're going back through a partial image of something that you could possibly remember from a 2-second glance you took as the car was going away, and you actually don't know if you can know the license plate number, unless you actually, in the case that you don't purposely write down the license plate or look at the license plate, you may have seen it anyway, which is what they're trying to get at. So usually what ends up happening is the human brain goes back and looks and says, I don't know, did I see it? And you start to think, what was I looking at? And then usually, if you think about it enough, you can put the pieces together. you come close. So that actually is part of the memory synopsis, as part of the Hopfield network that takes and looks at partial information and completes it with analysis, so that if we were a computer artificial intelligence program, we might actually get the full license plate out of that. Might not be accurate, but we can get some close resemblance to it. Here's other pictures of a bug, of some bottles of a drink, some dog pictures, where we could start from a small glimpse to a more refined glimpse by filling in the pieces. We fill in the pieces with our mental synopsis, which is how the neural network works. So we use our own natural associations. So auto-association, or context addressable memory. So the association would be, as an example of the license plate, I saw something and it looked like an L, or was that a 6? You know, it's a number. So the L and the 6 are sort of close if you think about it from a memory perspective. Or a T, could that be a 1? Look like a T. You know, and then you're then that's when you start playing around with the numbers and you associate glimpses of something you may have seen with numbers. So it's kind of like how people mistake balls that go out into the street. You know, that looks like a ball, because your brain is going to go, oh, looks like a ball. I'm supposed to be looking for a ball. But really it wasn't a ball, it was an animal or something that went out. But the response is good, because hopefully you stepped on the brake for both. But that's associative learning through Hopfield networks. So he applied it towards a computer artificial intelligence system. The task itself was to store images from resolutions of 20 by 20 pixels and do image recognition. So Hopfield's network with 400 nodes. So there was a memorization part of it where you present an image, and then you apply the HEP rule to it, and you fill in the blanks, and then you go back to 1. Present an image, apply it, go back to 1. And in the recall stages of it, you present incomplete pattern when you recall it, and then you pick random nodes and update the pattern to fill in the pieces, and then you go back until you're settled with the results. So you can actually, from a memory, go from the left to the right here and build in the complete picture, from 1 bottle to 2 bottles. So memories that are attractors in state space that attract other pieces of memory. So probably everyone in this room is familiar with the concept of déjà vu. That's a neural network characteristic. You have déjà vu when a memory somehow is associated with another memory. You heard the same. People get it with sound, and they also get it with sight. So you can get déjà vu sight, like, haven't I seen you before? Well, you probably have seen that person before. If you think that you've seen that person before, you have. Or you go, haven't I been in this position before? Like you're having a conversation with somebody and all of a sudden you think, whoa, like we've been here before. We've done like déjà vu. So, which is where that comes from. Well, that's a neural network. That's an artifact of a neural network, which we can actually put in a computer science program and artificial neural networks as well, in which we're attracted to certain pieces of memory given certain other node synopsis. Like our brain makes a connection for us without telling us, because we didn't déjà vu is not conscious. It's an unconscious neural synopsis that occurs to provide a connection because we might need it. Because we have this concept of working memory, and our brain actually comes up with the information before we think it does, because it's faster than we are. So we might think, I want to say the word the. Well, that was already in my working memory and ready for me to go instantly. So now sometimes you see people with brain injuries, and the words come out wrong. They think a certain way. They go, I want to say the sentence, the boy walked down the street. And instead they say, the street walked down the boy. But I'm thinking the boy walked down the street. It happens with dyslexia. Happens with people read. They speak okay, but when they read it in, the brain takes it in, and it puts it out in the wrong order, or it switches it around. It's because of the synopsis. It's because of the neural network that has a slight flaw. It's not really a flaw. It's a training issue. So they can cure dyslexia. They can actually cure that other brain disorder as well through reconditioning. Because what you're doing is you're taking the neural network and you're training it through supervised learning, reconditioning it, and reoccurring it. And you basically fix it. So all that stuff is actually fixable. So unfortunately, not everybody in the world knows that, so they go around, spend their entire life with dyslexia not knowing that, or they have a learning. Happens with learning disabilities all the time. They don't understand it can be fixed. Same way as eyes can be fixed, but that's not neurology. That's something completely different in some cases. So catastrophic forgetting. This is the interesting part. We can actually make ourselves forget things as well. The problem is memorizing new patterns corrupts the memory of old ones. So people who cram for exams, this is why you should never cram for an exam. It's too late for you now because you would have done this last night and you would have already crammed. But usually it's undergraduate students that'll do this. They'll take and load up a bunch of new stuff because they haven't studied all term. They'll wait till the night before the exam and then they'll cram. Cramming for exams will reduce your score by 2/3 at the worst catastrophic case. It's going to damage your performance on the exam. It's not going to help you at all. Because here's why. You fill it up, your working memory, and you fill up the synopsis. It's like, think of it sort of like an electronic component. You're heating up a certain section, and the other sections are getting colder. And you're putting more focus and more concentration on this heated section. And the heated section is going to blur and corrupt the rest of it. So it messes up the pattern. If you have the same consistency of heat throughout the entire brain and everything is at the same level, better synapses, better connection. So even if you don't remember it, you don't have to worry about it. You'll find it. You'll find it through the memory by remembering certain other things that will lead you to that conclusion. So like when you don't know the answer to something, quit thinking about it. So you see something that says, what is the answer to this? The more you think about it, which is going back to that other theory, always accept your first impression. Your first impression has a higher likelihood of being correct. It's the people who start thinking that start rearranging the synopsis and putting focus on wrong areas. You lead yourself to a bad answer. And you actually take a good answer and you make it wrong by thinking about it. So if you want to do well on an exam, don't think. And don't memorize and don't cram the night before. Instead, what you're supposed to do is spend the last 4 weeks or the last 6 months or whatever, how long the class is. On day number 1, you cram. On day number 2, you cram. On day number 3, you cram. You put all the stuff in there and then you let it marinate. And you let the synopsis work. And then you come in and you get enough sleep so your brain's actually working correctly. On a cold system, you have a better likelihood of actually doing better. You're going to remember more, you're going to be able to actually function correctly. When you mess up the synopsis, you've messed up the entire system. And you can mess up the synopsis during the exam by causing confusion, by self-doubt, and by thinking too much. So don't think, and you'll do better this afternoon. For those people who read the chapter last night, that's a good idea, as long as you didn't sit there and start memorizing stuff. That's cramming, and you're going to cram crap in there. The stuff you cram in there creates a roadblock for everybody else. Everything else that's in the system that's going to try and come out, but it can't come out because you've blocked it with all this garbage you stuck in there last night. So. All right, so old memories cannot be recalled, or spurious memories arise, or a thing on the right now in front of you, you can't read it. It doesn't come up. So the solution, allow Hopfield network to sleep. Rest it. When the sleep mode puts it all back down to normal, makes it all the same temperature. Makes it all the same. Your brain actually does have what's called hot spots to it. You ever seen one of those? It's actually kind of interesting. Those psychic people, they do this thing with the aura. You see, it's heat related. So certain parts of your brain will heat up naturally under certain situations. Stress will heat up a certain part, which causes neurological disorders because you've hit a certain area of your brain and you've constantly stressed it. You're under too much stress, right? Here's what happens under stress. This is not the complete answer. This is like the Reader's Digest version of it. You're constantly heating up a particular area of your brain. Well, that area is going to get clouded and you're going to have what's called the same problem you have right here. You're going to have a catastrophic forgetting, which means you forget. And you're going to forget this, you're going to forget that. People who are stressed out can't think. They can't remember anything. They can't think. They forget everything. And you wonder, and when you're not stressed out, you remember everything. You can think clear, everything works better. And you're more productive, which I never quite understood why people get stressed out. It's natural reaction. It's nothing, but if you can control it and not get stressed out, you'll perform better. Anyway, long story short, because it causes a roadblock again. Not only that, but in the long term, causes other biological functions because your thinking's not working well, the rest of your system's not working either. Other things aren't working. So people who get stressed out have high blood pressure, bad cholesterol, but the biological functions don't work either. Not just your short-term memory, it's everything else that's not working right. You're introducing problems. So live happy. Be happy. Don't be stressed out. And you'll have a more productive life. You'll actually earn more money and have a more successful career the less stressed you are. All right, 2 approaches to, what was I talking about? Catastrophic forgetting still as well. Unlearning. Can you unlearn? Good question. Yeah, just stop thinking. Yeah. All right, so recall old memories by random simulation, but use an inverse hub rule. Well, you're going to do the connections backwards. Make room for new memories. So Bastin's an attraction and shrinking possibility. Well, you make room for new memories by not cramming it in and by not trying to remember. Actually, the more you try not to remember when you're trying to remember, the more you'll remember, actually. So trying not to remember it and having it come naturally actually kind of works. And then we have pseudo-rehearsal. This is what people do when they go, oh, I have to give a speech, so I'm going to start reading my lines over and over and over and over and over and over and over again, because that's the only thing I'm going to remember right now, because right now I have to remember those lines. So while learning new memories, recall old memories by a random stimulation. So the way you do that is not by repeating stuff, it's by going, okay, let's do the end. Let's do the beginning, and do it out of order. Then you actually remember it better, because then you can take the stuff that's at the front and put it to the back and reorganize the list that you've got memorized, and then you can actually remember more by reordering it. Or use standard Herb rules on new and old memories themselves and restructure the memory. So it needs short-term plus long-term memory to restructure it. And on mammals, we have a hippocampus plays back new memories to that's a part of the brain, to the neurocortex, which randomly stimulates at the same time. So actually, everybody knows about random stimulation and you know about the restructuring, because while you're sitting here listening to me, you're also thinking about something else. Every one of you. Even I'm thinking about something else, because I'm restructuring. We're constantly restructuring. So here's what happens when you get tired. You can't restructure at the same rate. You restructure slowly. If you've ever noticed when you're exhausted and you're tired, you stop thinking. The number of random thoughts that are going through your head right now, if you're tired, are slower than if you've actually had 8 hours or you've had your proper amount of sleep, whatever your body requires. So, which means your cycle rate is faster because your brain's not tired. Your body's actually working at 100%. So you slow that down, you get tired, add that with stress, you can't think anymore either because you're not getting those random thoughts. The random thoughts are important. The random thoughts are, I wonder if I should go to the bathroom after the break. She hasn't done attendance yet. I'm sure some of you people have been thinking about attendance. The ones who came in later probably think, I wonder if I missed attendance. Some of you are thinking, oh, man, is any of this stuff going to be on the final? Yeah, I don't know. What about all those assignments? What am I going to do tomorrow? What am I going to do tonight? Geez, I'm thinking about sushi today for lunch. All this stuff is going through your heads. It is, guaranteed. I was thinking about sushi 5 minutes ago. I said it because I said it. It was definitely in the recent memory. Which is kind of interesting because that's why they do this stuff. They show pictures to people and they say, what does this picture remind you of? And depending upon what you're saying, they're supposed to be able to diagnose. They're using that recycle, and they can tell how often you're recycling by how the variance of your responses change. So there's little games that you can play with that as well. But unlearning and then pseudo-rehearsal, psycho-rehearsal, and recycling, and then moving things around actually helps you remember things. So which is kind of interesting because you could have knowledge on a particular topic. You could have taken a class in math before and know the information. And then you take another math class on the same identical topic, and believe it or not, you're going to learn more than you learned in the first class. Because the second class is going to go, well, my first teacher didn't teach it like that, but yeah, I see it now. And you've reorganized it, you restructured it. You're going to know it twice as well as when you originally took that class. which is how people who play sports, you just play sports every single day of your life, the same sport. And even though you've played it before, you've made that basket, you've made the hoop, or you've done the soccer thing 20,000 times already. But if you don't continue to do it, you haven't learned all the possible different ways. And you get to a certain point where you take the third or fourth math class is not going to help you because you've already restructured it enough. And then you move on to the next topic. So repetition actually helps with restructuring. All right, so in terms of the neural networks as a central pattern for pattern generators and generation, we use this in computer graphics all the time. And we also use it for other type of pattern matching in computer models and simulations all the time. So we can group neurons by creating rhythmic muscle activities, locomotions, heartbeat, etc. Identify several different vertebrates and introverts, and it's hard to study this particular area because then what we're looking at is trying to mimic for computer modeling something that might be a little bit more dynamic than a computer can actually handle. So let's see. Evolution of bipedal walking as an example, another experiment that was done. These are what I'm going through right now are just some example things that have been attempted to be solved by artificial neural networks. Looking at the patterns in terms of walking and things, actually they can tell muscle problems, muscle growth, muscle maturity, and someone's physical health by the way that they walk. You can also tell the back structure by the way somebody walks as well, because you can run it through a process of synapses and you can tell what the person's thinking about by the way they're walking, so which is kind of interesting, or how the person's thinking by their body positions as well. So looking at the graphs themselves and the actuators in the space, it's the same concept as before. So summary, long story short, to conclude your overview of neural networks, from a non-technical perspective, but from an artificially intelligent approach, we have the different components. The components are going to be the nodes or the neurons, and then the synapses or the weights between the nodes. Node adjustment, do not interfere or do not perform a memory analysis that connects that at all to Bayesian networks. Totally different concept completely, which is the common neurological failure that people will do is they'll go, oh, information, another information, put it together. It's like when you hear the same term but it's used in different contexts. This is a different context. Feed-forward networks, not to be confused with forward and backward chaining done in traditional style networks. A little bit different. Forward and backward chaining works with a pattern, usually on a context, and there's a route that's taken that's a definite route. With a neural network, it can be changed through the hidden layers of analysis that we don't actually see. It is not an algorithm, but it's an analysis. So we have unidirectional flow of information that's going from point A to point B. We don't know which direction it's going to go. Your decision is going to be based upon your synapses. And it's good at extracting patterns and generalizations and predictions. And it basically turns into our pattern behavior through our natural learning. And the distribution representation of the data and the ability to represent the data is also equally important. Parallel processing of the data that happens. So Bayes networks don't do parallel processing. They do sequential forward and backward chaining. Neural networks do sequential processing. You do. If actually just compare your brain and your thinking, you do parallel processing. You're processing everything simultaneously. You're not doing it in a sequence. Training. We have to do training, back propagation. In a computer science perspective, our humans, that's our learning process. We are training the network, so to speak. And not exact models, but good at demonstrating principles. So we can take the concept, implement them into an artificial intelligent computer program to a certain point, but we're representing a science of biology with algorithms and data structures, which is slightly different representation than reality. And there's about 5 or 6 different interpretations of this. Not everybody agrees, actually, with the science. We also have recurrent networks, which I talked about, multi-directional flow of the information, using recurrence and currency as a factor. Memorizing sense of time, complex temporal dynamics are also part of this. Various different training methods and also different models, as we've seen before. So I am going to stop this lecture on artificial neural networks and talk about other stuff.